Hi, this is Dr. Xu teaching mine ventilation for mining engineering college students. In this video, we will talk about the gas laws and the related gas calculations. Firstly, we will look at this ideal gas law. So it is PV equals to nRT. P is the absolute pressure in Pascal. V is the volume in cubic meter. N is the number of moles. So number of moles equals to the mass of gas divided by the molecular weight of the gas. R is the universal gas constant. So it is 8.3145. T is the absolute temperature in Kelvin. So Kelvin equals to 273 plus the Celsius degree. So if we expand the N here to mass divided by the molecular weight, we have PV equals to M divided by the capital M by R and T. So we can move this V to the right side of the equation and everything else to the left side. We have got M divided by V equals to P M divided by RT. M divided by V is the density. So we have the density equals to pressure by molecular weight divided by universal gas content by absolute temperature. To calculate the density of a gas mixture, if individual gas density is known, then the gas mixture density equals to the sum of the concentration by the individual gas density. If individual gas density is unknown, then we can use the molecular mass of the gas mixture. We can calculate the equivalent molecular weight of the gas mixture by adding up the concentration of the gas and the molecular weight of that gas. So add up all the gases here. Now we have the molecular weight of the gas mixture. Because we know density equals to pressure by molecular weight divided by R and T, so we can calculate the density of the gas mixture. Let's look at one example. 40% of CO2 mixes with 60% of CH4 at standard temperature and pressure. So standard temperature is 0 degrees Celsius. Standard pressure is 101,325 Pascal. What is the gas mixture density? Molecular weight of carbon is given, molecular weight of oxygen is given, molecular weight of hydrogen is given. So the first step is to calculate the molecular weight for the individual gases. Because we don't know the density of CO2 and methane, so we will need to use the method that calculates the molecular weight for CO2 and methane. So for CO2, it has 1 carbon and 2 oxygen, so the molecular weight is 44. For methane, there's 1 carbon plus 4 hydrogen equals to 16. The next step is to calculate the molecular weight for the gas mixture. So the gas mixture equals to, so this is the molecular weight for CO2, and we have 40% of that. And this is for methane, we have 60% of that. So the molecular weight equals to this. Lastly, we need to calculate the density of the gas mixture. So the equation is density equals to Pm divided by RT. So pressure is 101,325 and molecular weight of the mixture is 0.027. Divided by R is the constant T. Standard temperature is 0 and we convert it to Kelvin. The result is 1.21 kilogram per cubic meter. Let's look at another question. Compressed air is being reticulated at a pressure of 700 kilopascal, 25 degree and 1.5 kilogram per second. If the density of air is 1.2 at 101.3 kilopascal and 20 degree, what is the volumetric flow rate in the pipe? So I ask you to pause the video and spend about 5 minutes and work on this problem before you continue watching the solution. Okay, please pause the video. Okay, there are a couple ways of solving this problem. I will show you one of the ways that I have used to solve the problem. So at normal density 1.2, we can use this equation. The density equals to pressure molecular weight divided by RT. So at 1.2, we have P equals to 101,300 by M divided by R. Temperature is 273 plus 20 degree. So at this density, we have pressure of this and temperature of 20. At higher pressure, we have rho 2 equals to 700,000 by M divided by R. Temperature is 273 plus 25. So this is the pressure and this is the temperature. Now we can divide the first equation by the second equation. So 1.2 divided by rho 2 equals to 101,300 by M divided by R, 293 divided by 70,000 M divided by R by 298. M cancel out, R cancel out, so we can solve this rho 2. It is 8.15 kilogram per cubic meter. So lastly, we need to calculate the volumetric flow rate. We know that the mass flow rate equals to volumetric flow rate by density. And we know the mass flow rate is 1.5 kilogram per second. So 1.5 kilogram per second equals to volumetric flow rate by 8.15. Solve for volumetric flow rate that equals to 0.18 cubic meter per second. So we have solved this problem. There are other ways of solving the problem, but the basic idea is either by using the ideal gas law or using this density equation. Lastly, let's briefly talk about how do we monitor gases. One of the basic tools is the gas indicator tube. So different tubes are for different types of gas. When we use it, we need to break the two ends of the tube and push air to the tube. There is a chemical material that changes color according to the gas that measures. So we can read off the concentration based on the color indication lines. Nowadays, the portable electrical gas monitors are more common. These monitors are handheld. Most of the times, it can read the concentration of multiple gases. Another gas monitoring system is the tube bundle system. So on the surface, you have a gas analyzer and calibration tanks. It could be a movable camper-like room. In this room, it has ability to measure the concentration of different gases. And you have a pump there that pumps gas out from these tubes that connect to different places of underground. So gas will be pumped to these tubes to the analyzing room so the concentration can be continuously monitored. It needs to be noted that although it's continuous monitoring, there is some delay because for air to travel from underground here to the surface here, it takes time. So the reading of the concentration on the surface might be the concentration happened a couple minutes ago in underground. Depending on the flow velocity in the tube, we can calculate the travel time from underground to surface. And then the delay time, if we know the length of the tube, that divided by the velocity in the tube, we can calculate the delay time. The next method is by using gas chromatography. The gas chromatography equipment is set up in the lab on the surface. By taking samples from underground, you can use this little tube. It's a vacuum tube that used for drawing blood, for taking blood sample. But in underground, we can use a needle to punch here So gas can be filled in this vacuum, and after finish, we remove this needle out. The sample can be collected. This is another type of vacuum bottle, and we can also use plastic bags to take air samples in underground. Once we bring this to the lab, we will need to take a little portion of the air sample using this syringe and inject it to the gas chromatography. And this gas chromatography can read off the concentration of the gas that you are interested or the concentration of multiple gases. By using these automated arms or the automated arms here and the rotating sample holder here, and this is sample tray, you can program it for the gas chromatography to take samples from these sample trays and keep injecting to the gas chromatography for analyzing. Another sampling technique is the use of solid phase macro extraction. So in short, SPIMI. SPIMI is a novel, better device for gas sampling. It hasn't been widely used in mining applications, but it has great potentials. So it looks like a syringe with a needle here. All the top parts are mechanical parts that help to push or pull back this small fused silica fiber. This fiber is where it takes gas samples, and gases will be adhered to the stationary phase film. The benefit of SPIMI is it can take samples selectively. If you have a gas mixture of A and B, by selecting the right fiber, more gas A can be absorbed onto the fiber if gas A is what you are interested. So it can increase the sensitivity when you analyze the sample using the gas chromatography. Another benefit is it can be directly injected to the GC. So it eliminates the intermediate process error. I have done some study of using SPIMI for taking mine gas samples. It looks a simple device, but there are many aspects to study. For example, you need to find the right fiber to take certain gas samples. You need to study how long it takes for the absorption to achieve equilibrium. This is one example where we need the analytical chemistry knowledge in solving mining engineering problems. So, in this video we have talked about the ideal gas law and how to apply it in gas calculations, and we have also talked about the methods for gas monitoring. This is Dr. Xu. Thanks for watching this video. Please like, subscribe my channel and share. I will see you in the next video.